Recording is rolling. It is Tuesday, December 13th. We're going to continue with this review. You guys should have this half page of about 100 conceptual questions. So we're going to focus on these today. If you don't have this for whatever reason, then here, I'll put a stack right out here. You guys can grab one of, oh, I did get this to you guys, right? Oh, here. Pass some of these around, pass some of these back. Okay. All right, so you guys got those. Remember, like a class like this, there's you have to be able to handle complex questions, be able to solve like college level G graphs, navigate algebra, trigonometry, geometry, and also understand like the questions we're going to be looking at today is like the core like fundamental conceptual understanding you have to have to. I mean, if you don't get these kind of questions, kind of hard to handle through some higher complex questions too. These are like getting at the big picture of the. So you guys remember your guys' midterm? Here, show you guys what I showed you the other day. There's going to be 50 multiple choice questions that are 1 point each. And actually, the questions that we cover like today and tomorrow is going to be that's where these are coming from, right? And then I will give you guys 10 multiple choice, more like traditional problems to solve. This is really gonna look like one of your quizzes, but it'll be like cumulative. So I went through each section. We've done 6 of the 7 official units in AP. So I just did one. I picked 1 or 2 questions for each section, and just yeah, so it'll look like one of your quizzes. Okay, you guys got that? And that'll be the other half of the midterm. Okay, you guys got that? All right, any questions about the format? That's gonna work. All right, so yeah, remind you guys where we are in the year 2. So AP has 7. AP Physics 1 has 7 official units. They used to have more. They used to like do some electricity stuff, which we'll touch on briefly, just so you guys are familiar with it, and that'll be spring semester. Right. But unit 1 is kinematic motion, right? That includes linear motion, projectile motion. Unit 2 is like dynamics, that's forces, Newton's laws of motion, that kind of thing. Unit 3 is like a few topics put together. There's centripetal force, there's universal gravitation, but you can put those 2 ideas together, you can get orbits. Right? Unit 4 was energy and energy conservation work. Right, so there. Unit 5 was momentum and collisions. Now, Unit 6 is the only one we haven't touched on yet. Unit 7 is rotational dynamics. That's one we just finished up. Right? Talking about torque, angular momentum, rotational inertia, also rotational kinematics. Right? So like rotation stuff. So actually, like these first 5 topics also we're going to have a duplicate analogous idea in Unit 7. Okay. Yeah, I think we probably will. So we'll hit all these questions and go back. If you have a specific question about that, then yeah, you do that. Right. So yeah, the big picture things. The only topic we haven't covered is Unit 6, which is harmonic motion. So in January, we'll do some pendulums. We'll look at relationships, length of a pendulum, the amount of time it takes to swing back and forth for pendulums. Okay? And then we'll have covered all this. And then what we can do is, like once we finish this, like halfway through January, we can take a few weeks to do a bunch of review. We can do a bunch of FRQs. I'll give you guys entire practice exams with the multiple choice. And then here and there, we'll touch on some of the topics that AP does not officially cover, just so you have be a little bit familiar with those. All right, I want you guys something else too. All right, so I just uploaded some links to Google Classroom for you guys. Now, I'm not going to assign you guys anything over Christmas break. I think Christmas break is important for meeting it with your family and recharging your batteries and working. I always like to work on personal projects. I always have like something going on that's like outside of like stuff I'm being paid for. So that's a good opportunity for that too. Right. But if you have some spare time, like I really need something to do. I mean, there's always stuff to do in physics. So I uploaded some links for you guys. We're looking at here. This guy, Alan Sowell, the STEM coach, he covers solutions to old, past AP Physics 1 FRQs. He does a really good job. We'll go through like 10-15 minutes, like, oh, yeah, here's a solution, blah, 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 blah. Okay? I like his style, and blah, blah, so I recommend him. Here's Khan Academy, of course. You guys are probably familiar with that, so I'll give you guys a very convenient link. Look at this: one-dimensional motion, two-dimensional motion, force Newton's law, centripetal force. Oh, look at that! Just go straight in the order of like AP topics, right? Just like we've done. We've gone right there, right? So that's all right there. Ooh, this guy like flipping physics. Yeah, he does a bunch of review videos for like AP Physics 1 now, right? Topic. So this guy's on angle on that. Sometimes what he'll do too is what I do sometimes in class is say, hey, here's the big picture of things and how things work, and then he'll point out specifically, here's what AP would ask, and here's like some extra stuff that's good for a big picture idea, but AP is not going to ask this or that question. So and then I also gave you guys actually this is to AP Classroom, so I've got this open in another browser over here. You guys remember too, sometimes I'll remind you guys point these out, these daily videos. Like for unit 1, looks like there are 14 videos, and then that's just unit 1, okay? So those are always there for you guys. So there's a bunch of resources, and these are all just links to like video type stuff, right? So that stuff you can find too. Okay? So that's there for you guys, so you know that's there. All right, and then yeah, like I said, I'm just going to go down these questions, hit these one by one. And if you guys do have any other specific questions lined up there, then go ahead and hold on to those. And we've got a few days to review. All right. So first question, when you look at the speedometer of a moving car, you can see that car's what? Yeah, velocity at that instant, right? It's like an instantaneous velocity, right? Now there is also a type of velocity we don't talk about very often here, which is average velocity. Guys, is average velocity like total distance over total time? That's like if you went on a long road trip and you have like stops in the middle, right? Okay. But yeah, this is an instantaneous velocity, isn't it? It's like at that instant, okay? Which is usually all we talk about anyway, like V naught, V final, those are instantaneous values. Okay? See, a train travels, 6 meters per second, 6 meters the next second, 6 meters in the second after again. Ooh, does that sound like a constant velocity of like 6 meters per second? So here's the question: what is its acceleration? 0. 0 meters per second squared. It's not accelerating at all because it's not changing what it's doing. Okay. The car starts from rest and after 7 seconds is picked up to 42 meters per second. Oh, what's the acceleration? Yeah, 6 meters per second squared, right? 7 times 6 is 42, right? Is that like V final equals V initial plus AT, right? That's that second kinematic equation, right? VF equals V naught plus AT, right? You guys can figure that out, right? As an object falls freely in a vacuum, let's see, is its speed increasing? Yeah, or if you saw an option say its velocity is increasing. In fact, its velocity is increasing how much every second? You say 9.8 or 10 meters per second per passing second, right? Okay. We're assuming you're on Earth, right? It's give an assumption. Okay. Is its acceleration increasing? So the short answer is no. The acceleration is just going to be constant. We're going to take it to be constant. Okay. Either constant 10 or constant 9.8 meters per second squared. Okay. So acceleration is constant at free fall, velocity is increasing. Okay. In the absence of air resistance, objects fall at a constant acceleration. Acceleration, right? They'll pick up velocity at a constant rate, but that's what acceleration is. Yeah, constant acceleration, 10 meters per second squared, you can call it. Suppose an object is in free fall. Each second the object falls, would you say, see a larger distance than the previous second? Right? It could fall a constant acceleration. It could pick up 10 meters per second per passing second, right? It's falling but constant, it's picking up, it's increasing its velocity, right? So you could say with greater and greater speed, right? And you guys also know if you do like distance per time, like height per time, right? Like it'll only fall 5 meters in the first second, but then the next second picks up to like 20 meters, right? So isn't it falling like further every successive second, right? It's like spreading out in terms of distance versus time. Also true. A ball tossed vertically upward, rises, reaches its highest point, falls back to the starting point. During this time, the acceleration of the ball is always which direction? Which direction is the acceleration? It's always down because the net force is always down because the weight is always down. Earth is always pulling down, okay? And the net force will determine the acceleration direction. Ball is thrown straight up. At the top of its path, its instantaneous speed is 0 meters per second. a ball is thrown straight up at the top of its path. Its acceleration is 9.8 or 10 meters per second squared, right? That's true the entire time it's a free fall, going up, coming down, like we're assuming in a vacuum. A car accelerates at 2 meters per second squared. Can you guys see that needle moving? It's picking up 2 meters per second every passing second. Assuming the car starts from rest, how much time does it need to pick up to 20 meters per second? 10 seconds, right? Is that VF equals V naught plus AT? Right? V naught is 0 meters per second. VF is 20 meters per second. Acceleration is 2 meters per second squared. I think you need 10 seconds, right? 2 times 10 is 20. Freely falling object was put with the speedometer, so its speed reading would increase each second by how much? Yeah, about 10 meters per second. Picks up 10 meters per second every passing second. It's 10 meters per second, 20 meters per second, 30 meters per second, 40 meters per second. A freely falling object starts from rest. After falling for 6 seconds, it will pick up to what speed? About 60 meters per second, right? Yeah. It's going to pick up in speed 10 meters per second every passing second. Ooh. So the speed is changing, but the acceleration is constant. Let me show you guys. Let me find that table of a ball falling off a cliff. Here we go. Share the screen here? I think so. All right. So you guys remember a ball falling off a cliff? Right. Here's the acceleration. It's the same all the way down. That many meters per second squared. Its speed, therefore, is picking up 10 meters per second or passing second. So it goes 10, 20, 30, 40, 50 meters per second. Okay. And the distance is the one that spreads out. Right? Only 5 meters during the first second, and whoa, now it's really picking up. Okay. So if you graph x versus t, they'll make a parabola. Something like that. Okay. And the equations that back that up are those right there. Right? Guys remember that? All right. Back over here. Okay. So starts from rest after 6 seconds, picks up to 60 meters per second. Okay. Ball starts to the air at some angle. Ooh, maybe think like a projectile, like a parabola path. At the very top of its path, its velocity is, so you throw something in the air. At the very top, is it going strictly to the side? Is that entirely horizontal? Right? It'd be entirely horizontal motion, right? Also, would have the slowest speed at the top, right? It's like slowing down on the way up and then speeding up on the way down, right? So yeah, it has 0 vertical component velocity, but it's moving at the top. It's just moving strictly to the side, strictly horizontal. Right? You say v in the y direction would be 0, okay? But v in the x direction is the same all the way throughout the flight. A falling through into the air will never go as far as physics ideally would predict. So we can sit down here and do these equations, and then let's say we go out into the field and like throw some tennis balls, and they always land a little bit short. Okay? Mainly because of why?
Air drag.
Air drag. Yeah, because that's we make some simplifications for this class. That's kind of a big simplification, right? Air drag. Right? We're ignoring that. Airplane flying into a headwind loses ground speed. Airplane flying with the wind gains ground speed. Right? Is it fighting the wind or is it getting boost from the wind? Right? But what if the airplane is flying at right angles to the wind? If you watch it shadow across the ground, or somebody standing on the ground pointing a radar gun up at the plane, what is its ground speed compared to, say, what its engines are making it do? Give you guys a hint. Let's draw this up. Let's say the plane, the engines can push against the wind and make it go like 40 meters per second. Okay, that's how. So through a velocity vector there. Okay. There's a plane, 40 meters per second. Okay, and it's in a crosswind, and the crosswind's blowing straight east at like 30 meters per second. Now, if you're down on the ground, you point a radar gun at the plane. What's that radar gun going to read? It's not 30 and it's not 40. 50. Because they have to do Pythagorean theorem. Because there's the resultant right there. From that tip to that tail of that tip. Right? This is the resultant. You guys get 3, 4, 5 right triangle. Right? Yeah. So relative to the ground, the plane is going 50 meters per second. But it's not on we're like northeast angle. Right? So it's about 37 degrees right here. About for that particular geometry. Speaking of which, look at this. What is the resultant of a 3-unit vector and 4-unit vector at right angles to each other? 5 units, whatever those units are. Could be meters, could be meters per second, could be meters per second squared, could be newtons, could be kilogram meter per second, right? So anything is a vector. When in orbit, a satellite such as the space shuttle is, okay. Pause right here. All right, record and resume. We're here. When in orbit, a satellite such as a space shuttle. All right, we're looking for here. Could you say you'd be basically a projectile that's just falling around the curvature of the Earth? You could really say it's a projectile, right? Okay. But if you get in it fast enough, then it could actually follow in a circular or an elliptical orbit rather than a parabola. Okay. So I'm going to go with is a projectile for the multiple choice answer here. Okay. Space shuttle is like a projectile falling around the curvature of the Earth. After a cannonball is fired into frictionless space, the amount of force required to keep it going. Ooh, how much? Voyager 1 spacecraft, how much fuel does it need to keep going? 0. What's keeping it going? Starts with an I. Inertia. Right? So yeah, you need no force. No force. Right? It's just going. Inertia, right? No force. If the force of gravity suddenly stopped acting on the planets, what would the yeah, that is Newton's first law of motion, right there. Okay. So this question, I think it's best if I draw this out. Okay. So we got the sun, planet, here's the orbit, it's going around. Okay. Let's see, right at this moment, the gravity turns off. You guys tell me, does the planet fly off tangent to its motion, or does it make a random 90-degree turn and fly straight away from the sun? How many of you guys gonna say it flies off tangent to its motion, just like I drew it there? Yeah, right, that'd be the answer, right? Which is also Newton's first law of motion. I think we're in the Newton's first law of motion questions, right? Okay. A sheet of paper can be withdrawn under a container of milk without toppling it if it's stirred quickly, because that container of milk has a lot of inertia, right? A lot of mass, a lot of inertia, right? Now there's a multiple choice answer on this one that also says a lot of weight, which is proportional to inertia, but it doesn't explain this particular phenomenon, right? Like weight is a downward force, which should actually like sort of counteract this. Okay? So the fact that it has so much inertia, so much mass, just wants to sit right there. Okay? Did I show you guys the Paul Hewitt tablecloth trick? Maybe. I don't know. It's I put all the Paul Hewitt videos in a folder back on week 1 if you guys want to see it. It's a fun demo. It takes a tablecloth, it's covered in a bunch of dishes. He goes, pulls it off, all the dishes stay in place. Okay. The force required to maintain an object at constant speed and free space. Oh, we just answered this. 0 newtons, right? 0 newtons. It's just going. Voyager 1 spacecraft, it's just going. Equilibrium. Would you guys say that all the forces sum to 0 newtons? Okay. Would you guys say that's true in the vertical direction and also in the horizontal direction if you break it down into components? Okay. And recently, just in the last few weeks, we added one more condition, which is that the torque also sums to 0. But I think in this part of the chapter, you'd say just the forces sum to 0 in each direction, right? All the components sum to 0. A girl whose weight is 500 newtons. Pause right here. What would the mass be? How much mass? About 50 kilograms, you guys think? Okay. It hangs from the middle of a bar supported by 2 vertical strands of rope. What's the tension in each strand? Well, if she's right in the middle, then each strand must be how much? 250, right? 250 newtons, splits 250, 250. Okay. Now, if she wasn't right at the middle, okay, well, that's where you have to do some recent physics with torque and figure out, maybe it's like a 300, 200 split or something. But if she's right in the middle, it's 250, 250, right? Friction is a force that always acts, would you guys say to oppose the motion, right? Oppose motion, right? Friction is going to oppose the motion. What is the maximum resultant from 2 newtons and 8 newtons? Now, there's lots of ways you can combine 2 newtons and 8 newtons because these are vectors that they could be like 2 dimensions, 3 dimensions. So I could do 8 newtons and 2 newtons like this. I could do 8 newtons and 2 newtons like this. I could do 8 newtons and 2 newtons like this. Okay, those are connect those all tip to tail, right? Right. So, but really, it might be something like this. Like there's a ball set in the middle floor. I could do 8, 2, 8, 2, 8, 2. Okay, so lots of different ways, right? Which one of these shows the maximum resultant force? Yeah, right there, right? So 8 plus 2 is 10, right? So if I go both in the same direction, 8 plus 2 would be 10 newtons of force, right? Okay. This one would only be 6, and this one would be, whether Pythagorean theorem is something between 6 and 10. So between 8 and 10, I guess I could say, right? Okay. So 10 is the most. Okay, so those. A 100 Newton lantern is suspended by a pair of ropes, 120 degrees between them, 60 degrees from the vertical. What is the tension in each rope? Ooh, this is a good one. You guys should definitely be able to solve that. Here, let's draw this out. Okay. So I got a. This was actually similar to one of the slides the other day. Okay. So I got this lantern. Okay. Now the lantern weighs 100 newtons. So I'm going to put a down force of 100 newtons. Okay. And they said 120 degrees between ropes. If that's 120 degrees, then is that 120 degrees and that 120 degrees, right? Ooh, so it's like perfectly split. Or if you like, how about this? They did say that this right here would be 60 degrees, right? However you do it. Do you guys see the symmetry of this thing? I mean, if that's 100 newtons and it's in equilibrium, what do each of these have to be? I'm thinking 100 newtons and 100 newtons. Thinking everything's 100 newtons, right? Here, what if you took the way the whole frame of reference, you don't know which way gravity is, right? If you just ignore the lantern, blah, blah, blah. Okay. You see it's like a three-way tug of war. Suppose you're up in a helicopter watching 3 guys play tug of war, right? And this is perfectly symmetrical, 120 degrees between each of them. See, it's 100, 100, 100. Is that right? All right, now, what am I doing in this class if it's not so straightforward? Like, what if these angles aren't so pretty or both, right? Is can you break these into components? Say, well, these 100 Newton guys, you know, maybe they're unknown. Maybe you're solving for tension left and tension right. You say times cosine of 60 degrees to get the upper components, times sine of 60 degrees to get the right left components. Okay. Right left would have to cancel out. The two upwards have to balance with 100 newtons downward. Okay. But in this case, cosine of 60 degrees is 1/2. So got half of 100, half of 100, add up to 100. Okay. So different way of approaching it. It's the same thing, right? Okay, so break those into components. Do the whole thing. Right. That was the slide we did on the presentation the last couple of days too. Right. That was very similar to that. I think it had an apple hanging or something. A couple of spring scales. Which has more mass, a kilogram of feathers or kilogram of iron? And you guys say that they're both 1 kilogram. So they're the same. Now they have the same mass. Does that mean they have the same inertia? If you push on with the force, they'll accelerate the same? Yeah. Does it mean they have the same gravity force, the same weight? Yeah. The extension questions, right? Same mass. 1 kilogram is 1 kilogram. Right? Different volumes, different densities, but accelerations are produced by. Okay. So remember, first weeks of this class, we looked at what acceleration was. It was a rate change of velocity, right? And then when we got to unit 2 by AP's book, we said, well, what causes these accelerations? What's the answer to that question? Forces. Forces cause accelerations. Okay. So if there are multiple forces, you find the net force, right? Like the net force on this lantern would have been 0 equilibrium, but maybe if I was like pushing on this ball with like 8 and 2 newtons, you have to figure out, well, what's the net force, like which that direction. And then take over to Newton's second law of motion. Whatever the mass is that it's acting on is going to like decrease the acceleration, right? F equals ma, a equals f over m. How does the acceleration of an object change in relation to its mass? Okay. So, guys, the more massive something is, say for an equal force. Here, how about this? Give you guys a picture and some graphs. Right? Say I got like a tennis ball and a bowling ball. Right? Bowling ball is a lot more massive, okay? And we put the same force on both these guys. Right? So kick along and come along, kick it with the force. Say like a 50 newtons of force, 50 newtons of force. This is the same force. Okay. Can you guys draw a graph? Okay. So a ping pong ball in here. Let's throw so we're going to vary the mass in kilograms. And we're going to say, what is the acceleration in meters per second squared for a constant force? What would that graph look like? Good AP question right there. So constant force, put the same force on all these objects. Same force. As you increase the mass, what happens to the acceleration? Like that, right? Is that acceleration is force on that? Oh, look at that. It's Newton's second law of motion. That's Newton's second law of motion, right? Inverse relationship between acceleration and mass. Right? Right here. Okay. So we've got an inverse relationship between acceleration and mass. When an object reaches terminal velocity, so it's picked up so much speed, there's picked up so much air drag. You have to include air drag to get terminal velocity. Okay. What does its acceleration go to? 0. Yeah, 0 meters per second squared. Okay. So it's moving really fast. It's just moving down at constant speed, right? Because its weight and the air drag are balanced out. So equilibrium, right? 0 acceleration. A book weighs 4 newtons when held at rest in your hands. What is the net force? What's the net force of anything at rest? Yeah, 0. Yeah, 0 newtons, right? So the weight down 4 newtons, the force from your hands up collectively 4 newtons, right? 4 down, 4 up, 0 is out. Okay. See if we got any questions on any of these so far? You guys doing all right? Yeah. Okay. Girl pulls on a 10-kilogram wagon with 20 newtons of force. What's the acceleration? Yeah, 2 meters per second squared, right? A equals F over M. Okay, 2 meters per second squared. Object has constant mass. Okay. A constant force will produce a constant velocity or acceleration. Acceleration. That's Newton's second law of motion. I guess he has like a ton of Newton's second law of motion questions going on right here, right? Okay. So pressure. Is that force per unit what? Area? Force per area? You take a force, spread it out over an area. If you pump up your bike tires, you have an American pump. What's the unit on the American pumps? PSI, pounds per square inch. That's a force per unit area, isn't it? Okay. For this class, we usually use a metric system, so it's like Newton per square meter, also called pascals. Okay. That's force per unit area. Okay. There's about 100,000 pascals of pressure on you right now, just from the atmosphere. If the force acting on a cart doubles, what happens to the acceleration? Also doubles, right? So there's a direct relationship between the force and the acceleration. More force, more acceleration, right? Newton's second law of motion. Suppose the cart's being moved by a force. Suddenly, load is dumped in the cart so that the cart's mass doubles. What happens to the cart's acceleration? Half as much, right? Right? Here, let's do this. So we're applying a force to a cart, so mass, it's accelerating, so it's speeding up faster, faster, faster. Now we're gonna dump a bunch of groceries into it. We're gonna like double the mass. Factor 2 there. See how the acceleration is half as much? Okay. 20 Newton falling object encounters 4 newtons of air resistance. What is the net force? You guys say 16 newtons. 16 newtons, right? 20 down, 4 up. 6 Newton falling object encounters 6 newtons of air resistance. What is the net force now? Yeah, 0. 0 net force. Oh, I bet it's reached terminal velocity, right? 0 net force, it's at equilibrium. Go down at constant speed all the way down. Shoot. Right. High school student hits a nail with a hammer. During this collision, there's a force. Let's see. Is there a force on the nail? Yeah, there's a force on the nail. Is there a force on the hammer? Yeah. But which force is bigger?
They're the same.
They're the same. They're always the same, right? Got a force interaction between 2 objects. That's Newton's third law of motion, isn't it? Is that Newton's third law? Okay. You guys think we're about to get a string of Newton's third law questions? Okay. For every, so we're talking about 2 different objects. They're pushing on or pulling on each other. The force is always the same. Okay. Now the effects might be different because they might have different masses. Accelerations might be different, but the forces are the same. As a ball falls, the action force is the Earth's mass on the ball. Earth is pulling on the ball. What's the reaction force? The Earth pulls on the ball pulls on the Earth, right? If there's multiple choice option, something about air drag, that's a third object. We don't care about that, right? That's something else. Okay. So the Earth and the ball are pulling on each other, right? Whether it's in a vacuum or air drag, that's an equal and opposite reaction pair. Unfortunate bug. I got 2 questions about this unfortunate bug. Against the windshield of a moving car, compared to the force of the car on the bug, the force of the bug on the car is
Same.
The same. It's the same force, right? It's the same force. Right. Follow up. This spider bug's making an encore. Oh yeah. Compared to the it says deceleration. You could just say acceleration or negative acceleration. Right? The rate change of motion of the car. Right? The deceleration of the bug is what? Much greater. Right? It's a much greater change of motion of the bug. Right? Because the car has so much mass that it barely changes motion at all. Maybe it slows down a tiny bit, but you wouldn't even like notice, right? Unless you ran to like a million bugs or but yeah, from the bug's point of view, right, it has a huge change in motion, right? Same force, different masses, different accelerations. Okay? Inverse relationship between these two. Large truck and a small car, same speed, have a head-on collision. The vehicle to undergo the greater change in velocity will be the what? The small car, right? Okay. Now the force between them is the same. The smaller mass car has greater acceleration, therefore greater change of velocity. Okay. I'm saying acceleration, but I'm really talking, that could be any direction, right? It could be slowing down acceleration, right? Two people pull on a rope in a tug of war. Each person pulls with 400 newtons of force. Let's see, two people pull on a rope, 400 newtons they're pulling with. The tension of the rope, therefore, is, I guess, gonna say 400 newtons. Guess what? Take it right, 400 newtons. Right? Everybody's pulling 400 newtons. The tension's 400 newtons. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is the same. Right? Equal and opposite force pair. Two objects pushed on each other. Okay. Follow-up question. Compared to the impulse on the ball, the impulse on the launcher, is that also the same? Yeah. You guys remember impulse? That's change of momentum is what impulse, change of momentum impulse. Okay. You could say mass times change of velocity. Okay. You could say, well, where does that come from? Well, it comes from applying a force for some time interval. Right? So if the force is the same and the time interaction is also the same, then the change in momentum is also the same. Right? It just falls straight out of Newton's third law of motion. Okay? Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small, true, because why? Because the cannon has so much mass, so much inertia. Okay. You could say m times delta v of the cannonball equals m times delta v of the cannon. Right. Different masses, different delta v's. It's like the end process of Newton's third law stuff. They both have the same change of momentum, just different masses, different final velocities. A piece of putty. Oh, do I only have one of these? Okay. With 2 units of momentum, strikes and sticks to a heavy bowling ball that had been initially at rest. The putty sticks to the ball, and both are set into motion with a combined momentum of, are you guys gonna say 2 units? 2 units, right? Okay. I can't believe I left this other question off. We're gonna do the other question too. So we've got the putty, out here, and the ball. If it's flying with 2 kilogram per second, then both roll off together. Right. Inelastic motion with 2 kilogram per second. Okay, just like that. Okay, that's what we just did. Okay. Here's the question I should have shipped it on there. What if you have a bouncy ball coming with 2 kilogram per second? And the boing bounces off with let's say 1 kilogram per second in the opposite direction. Okay. That's going to set just the bowling ball itself off with how many units of momentum? 3. Right? Because one of these guys is negative. Do you guys see 1 minus -2 is like a change of 3? That's an impulse of like 3 units. Okay. So yeah, so the bowling ball gets off rolling faster with the bouncy ball compared to the putty. Okay. Yeah, we did this before. It's in your notes way back in the day. Right. 2 kilogram ball thrown at 3 meters per second. What's the ball's momentum? It's gonna say 6 kilogram per second, like mass times velocity. Okay. In physics, work. Ooh, looks like we got to the energy section right here. Work is defined as force times distance. Okay. When you guys get the AP exam, you're gonna get plenty of graphs that have here. Look like this. You're gonna get force in newtons here. You're gonna get distance in meters here, or some variation of that. Okay, and maybe you'll get something like maybe like a variable force. Maybe it's experimental, so you have like all these dots that are like kind of lined up, but kind of like that. Okay. So you guys just said work is force times distance, right? Okay. Now, how does that translate to a graph? What property of that graph is it? Area under the curve. So what I would do is like make this line, say, oh, look, this looks like a trapezoid. Split this up into a triangle on top of a rectangle, add those areas together, and that is the work, which is the energy transfer. Okay. Then you might have, if you have something going uphill, maybe that transfers into its potential energy. You have like a car on a flat track or a rocket in space, maybe that translates into its kinetic energy. 1/2 mv squared, something like that. Okay. Nellie Newton pushes with twice the force for twice the distance. She does how many times the work? Ooh. 4 times. Okay, because the work is force times distance. Okay. And you double this and you double this. That's 2 times 2, right? If it's twice the weight for twice the height, for example, yeah, there'll be 4 times the amount of work. Power is defined as what? Yeah, work over time, right? How much work, how much time, divide those, work over time. Okay. What's the unit for power? Watts, right? So energy and work are measured in joules. Right? Joules per second is watts. Right? So this could be joules, this could be seconds, this could be watts. Right? Capital W. You gotta be careful about capital W, right? Because it might mean work, might mean watts. Sometimes it means weight, right? But as a unit, it could be watts, right? Hey, do you remember I taught you guys a sneaky formula for power that there's a good chance could pop up on the AP exam? Is work force times distance? Time? What is distance over time? Velocity? Okay. What if you have an elevator moving up at some velocity? Can you say power equals force in the elevator cable times the speed of the elevator? Force times velocity? Now, that one's a good one to hold in your back pocket. I mean, it's real short, and it's not on the AP equations. Right? They don't give this one to you, but I've seen it pop up in the past. So, fair game for the actual AP exam in May. The amount of potential energy possessed by an elevated object is equal to, do you guys know the formula for potential energy? MGH, right? MGH. Okay. In the review last few days, I showed you guys the more universal formulas too, but this is really one that you guys want to focus on, right? It's localized to the surface of a planet. Okay. MGH. Okay. So it could be like weight times height, right? Maybe the weight of the object times how high you lift it. Phrase that different ways. MGH. How much further will a car traveling 100 kilometers an hour skip compared to 150 kilometers an hour? By the way, that's about 30 miles an hour to 60 miles an hour. So basically, you're doubling the speed of the car. Right? So what happens to its braking distance?
4 times.
4 times. 4 times. Okay. This is one of these questions that comes up over and over again in this class. So let me set up an open system. Let's sum of energy initial minus the work. That's not equal, that's a minus. Oops, sorry. Minus the work is equal to sum of energy final. So we start off with some 1/2 mv squared minus friction force times distance equals 0 joules if it comes to a complete stop. Okay. Now, if you change the speed of the car, the friction force doesn't change. Okay. So what's the relationship between this guy and this guy? It's a square relationship. Okay. Yeah, so just have this term over. Okay. Yeah, so if you double the initial speed, you get 4 times the braking distance. As a pendulum swings back and forth, would you guys say potential energy converts to kinetic energy on the way down, and kinetic energy goes back to potential on the way up? Right? Would you say it's all potential energy at the ends? Would you say it's all kinetic energy at the bottom? Or that's probably the easiest way to say that. Okay, you guys can do all that. Okay. So all this would be true, right? When a car's speed triples, what happens to its kinetic energy? Oh, here's kinetic energy right here. So if you triple the speed, kinetic energy increases by a factor of 9. 9 times, right? How about this? What about the car's momentum? If you increase, triple the speed, what happens to the car's momentum? increased by a factor of 3, right? Because momentum is just mass times velocity. Okay. Kinetic energy won't happen to be squared. Ooh. All simple machines ideally work on the principle that this was in the slides last couple days. You guys remember work input equals work output, right? So you can start from energy conservation. If you go back to the slides with the simple machines, I threw you guys a few slides, including the pulleys that you guys did for a lab. The first line is work input equals work output. Right? Energy is conserved. And you can break it down, force times distance, and then each of those individually changes. But the principle is that work input equals work output. Okay. How many joules of work are done on a box? Force of 25 newtons pushes at 3 meters. You guys say 75 joules. Work equals force times distance, right? Just everything's in a straight line here. Suppose you lift the box 3 meters, right? You've given it 75 joules of potential energy. Right? How much power is required to do 40 joules of work in 5 seconds? What do you guys say? 8 watts? 8 watts, right? Yeah, you guys do remember all these numbers have units attached to them, right? Right. Most of you guys are pretty good with units at this point in class, but every once in a while I see guys turn something that says like just say 8. It's not just 8, it's 8 watts, right? You guys say 8 what? From 8 gallons, 8 cookies, 8 watts. Which has greater linear speed, a horse near the outside of the merry-go-round or one near the inside? You guys would say outside. Yeah, the further out you are. Okay. Is that V equals omega times R? Right. R is how far from this point right here, right? This guy's about 1 centimeter. This guy's 4. Right? V is equal to omega times R. Yeah. Right. It's one of these posters hanging up here. Here. Which has greater angular speed, a horse near the outside or one near the inside? What do you guys say? Angular speed, is that like turns per time?
It'd be the same.
It's the same. They'll do the same turns per time, right? Same angular speed. Right? Different linear speeds, same angular speed. Okay. You guys got this so far? Okay. If you whirl a tin can on the end of a string and the string suddenly breaks, what will the can do?
Fly
off tangent to its motion, right? A lot like you turn off gravity, the planets will do the same thing. It actually sounds like a Newton's first law question, right? Centrifugal forces, notice that's in these quotation marks, right? Are an apparent reality to observers in a reference frame that is doing what? Like if you're in a car and you go around a curve, you feel like you're thrown to the side of the car because you're in a reference frame that is rotating, right? So that's what we're looking for, rotating. Right? Versus, here, suppose the car was like open top, right? And someone is in a helicopter looking straight down at you. Right? They say, oh, no, you're actually just trying to move in a straight line, and the car is like going around the curve, and the walls of the car are pushing you in, right? But so their centripetal forces always pull you in towards the center of the circle. A car travels in a circle at constant speed. Right? The net force on the car is pointed which direction? Yeah, it's always towards the center of the circle, right? Centripetal force always pushes or pulls you towards the center of the circle. Now, of course, if you're along for the ride, you think you're being thrown towards the outside, but really the walls are like pulling you in. When a wrench is slid spinning over a frictionless tabletop, the center of gravity follows. Would the center of gravity follow? Okay, we're talking about a frictionless tabletop, okay, spinning wrench. Does the center of gravity follow a straight line path? Yeah, that's the only point that would follow a straight line path. Okay. I've been using example classes. If you throw it in the air, it follows a parabola, but that's if it's a projectile. But yeah, it's just more simply over a frictionless tabletop. Center of gravity just follows a straight line path. Okay. Hey, is it gonna? Let's add one more detail. Is the center of gravity gonna go constant speed across the tabletop? Yeah. Right, so constant speed, constant direction, it's called constant velocity, right? That's the only point that would do that, center of gravity. Okay. Which of the falling is the center of gravity at a point where there is no mass. If there was a multiple choice option that said donut, would you guys pick the donut? Okay. There's no way donut looks like. You guys take the center of mass. So here's all the mass. Sprinkles. You guys think the center mass would be boom right about on that X, right where there's. Right? You guys think if you did you guys do with the foam boards on the string would always hang through the center mass just like that. And rotate this. Ah, center mass right there. So there is no mass. An object will fall over if its center of gravity is, what do you guys say, not over the base of support? Did I tell you guys that trick in class? Here, if you, or maybe like a challenge question. You guys ever put your feet back against the wall and try to reach out to your toes? Okay. Some of you guys may be able to do this, but it's really hard to do, okay? Because the soles of your shoes are like your base of support, and your center of gravity is somewhere around your belly button. If that base is, if your center of gravity ever goes outside the base of support, you're gonna topple over. It's gonna be a torque on you. All right. All right, yeah, well, Phil's about to rain here in about 30 seconds, so we're doing really good here. Okay. So tomorrow we'll finish up these questions, and I'll probably pull some more AP style practice with you guys too. Right? So, you guys, good review going into Christmas break. That's a pause point for today.